but never a reality. So thank you for that. And also, I have to disappoint you, Francisca, because tomography is number 3 on this list, and there's simply not enough time to really get into that. At the very end of this unit, we will look at tomography through the veil. We're not even going to, lift the tip of the veil, but we'll be looking at it through a veil. And there is a pointer to a resource that you might want to use to follow up on. So we'll primarily focus today in this last unit of ROSES 2020 on gridding and using inversion to do gridding, right? The same type of inversion that we would use for tomography. So the connection is natural, right, from going from inversion to tomography, as you'll see at the end. But first we'll talk about gridding, and we'll also talk about gridding without having to do an inversion. So bear with me as we go through these slides here. And also thank you for sticking around, for this last unit of ROSES. I know that for some people, your universities have already started again, after the Northern Hemisphere summer, and it is not easy, right, to stay in a summer school while you already are in your regular educational mode, right, where you're being graded for things. The great thing about ROSES is that there's no grades because it's all about our own learning here. And I have to say that I learned a lot from listening to my co-instructors as well. And also, to stay with the theme of ROSES, if you have any questions whatsoever, please don't hesitate to ask them. Any questions are welcome, and I will do my best to answer them. Type them in the chat box, and Francisca, interesting. Yeah, and Francisca will at some point interrupt me and read them out to me. So, as I said before, I can't cover these topics entirely. I'm just doing brief introductions to them so that you get a flavor of what's going on, and then you can follow up later and study, for example, the lab notebook in more depth and make variations on the theme. So I already said, please ask questions at any time. So our focus will be an example, and this example is all of these measurements of MOHO depth or estimates of MOHO depth that have been made for seismic stations in the United States, right? So this is a map of 48 of the states of the United States of America. And every colored dot here represents an estimate of the MOHO depth beneath that seismic station at that location where that dot is. And that MOHO depth estimate was made by a receiver function study, right? So these are sort of similar data that we heard about last week from Dr. Lowry. So that is our specific application. You have downloaded this data set, and some of you have mapped it already using your PyGMT knowledge that you learned from Liam Tony, to be Dr. Tony. So first, let me introduce this, the example, the general premise of gridding. So consider that you have a map, right? And this contour is, not intentionally resembling any particular country, but let's say you have some kind of region, right? Country or region that has measurements at some locations, right? These blue dots represent locations where we have measurements. In our example, these measurements are estimates of MOHO depth. And, but we want to get those measurements on a regular grid, right? Where we have a measurement every 1 degree, for example. Right, or every half a degree, for example. And that's mostly what this is going to be about, this lecture. But before I launch into the lecture, can you please give me some reasons why one would want to do this? Right? Why would you want to take a collection of irregularly spaced points where you have some kind of estimate or measurements, and why would you want to regroup them into a regular grid, as over here? By the way, can you all see my mouse when I move it? Right, a thumbs up would be fine. So if you can see my mouse, use a thumbs up. And if you have an answer to this orange question, type it in the chat, please. And Francisca will read them out.
Okay, we have a couple of answers here. So we have, it is easier for some algorithms to work with regularly spaced data. Another answer is for computational reasons, for synthetic simulation, to try and predict what is happening in between the measured points.
Yes, and those are all good reasons. And I had written down some notes for which I need to escape from this for a second. All right. Right, so yes, I think you hit the nail on the head. To define a continuous function of the quantity of interest via evenly distributed local supports, for example, through bilinear interpolation or splines between these regularly spaced support points over here. And why do we want to do that? So that, for example, we can average out errors in the data, right? We can quickly estimate a value anywhere, right? Like here and here and here, or in between these grid points, using this function that is defined by these support points that are a regular grid. Also, to compare the function, in this case of MOHO depth, to other known continuous quantities, for example, topography, or geologic terrains, heat flow, lithospheric thickness, density of the crust and upper mantle, right, as we learned about last week. And yes, you also mentioned that you can use this function, this sort of continuous function that is represented by the supports on this regular grid. We can use it to do forward computations over a whole region, right? For example, you can calculate the effect of the crust on surface wave propagation or on gravity anomalies anywhere, basically. So that those are all good reasons to want to go to a regular grid. So what if we have this situation, right, where we have points in these locations, but we have a large gap right here? So it will be hard, right, to predict what the data is in this region. So, but the gridding techniques that we're going to use here, at least the inversion technique that I'll sort of present, is will basically help you fill in some knowledge for this region. It might not be as much based on these measurements at these points, right, as the information in the grid in this region right here. But we can still add sort of prior knowledge, like from geology and independent information about what the MOHO should be in this area that is open gap. So gridding will help you deal with sort of spatial gaps in your coverage. Also, gridding will help you deal when you have a high density of points in a particular location right here. And it is possible that the data at these points, right, some of these points might fall, within the same, area of your grid. And the measurements might be inconsistent because of measurement errors and errors in the data that lead to the estimates of MOHO depth. So you can have gaps in your coverage, you can have inconsistent data due to errors. The inversion-based gridding technique will deal with all of those, all at the same time. So from this grid of support points, right, we can get to continuous functions of the MOHO. So let's say that this blue color represents a particular MOHO depth, and every measurement or estimate here is the exact same estimate. Let's say blue represents 42 kilometers, for example. Then we can interpolate between these points, and the whole entire United States becomes 42 kilometers, right? We have to define what that interpolation is ahead of time before we decide on the weights that we use for these interpolations. And I'll get to that. But it's also possible that each of these points has a different estimate of MOHO depth, and then we can get a continuously varying function, like over here in the lower right, that will change throughout the region. So let's say our MOHO depth is a variable y, and we can have discrete measurements of this MOHO depth or discrete estimates, like we had in the example that I just covered. But we want those measurements to be representative of a continuous function f that depends on the location, right, which is a vector x that consists of a latitude and a longitude. If you were doing tomography, this x would be a three-dimensional vector. It would have a depth component as well. But for now, we're not. X is latitude and longitude. And then there's some sort of estimation error that goes into these MOHO depth estimates. So we take this continuous function and we write it as a discrete sum over a set of basis functions times a weight. And so once we know these weights, we can express the value of the MOHO at any point x of k for any k, right, using this definition of the continuous function for the MOHO depth. Now, these basis functions are defined as a function of the location, and these weights, basically there's as many weights as there are basis functions h. So what about these basis functions? Well, there's different choices, right? We can turn h into some sort of polynomial, p of x. Or we can, instead of using polynomials of different orders, so I would represent the order of the polynomial. We could also use harmonic functions, right? So if we're on in a flat area, we can use sines and cosines, for example, in 2 dimensions. Or if we are on the surface of a sphere, then we can use spherical harmonics, for example, for these basis functions. But in this lecture, we're going to talk about these basis functions being local basis functions that are only defined in a local area around a grid point on a regular grid, right? And so then this basis functions is centered, for example, at x of I, and its value, right, it decreases as you increase the distance between the point of interest, which was x of k. We wanted to know the MOHO depth at x of k. And so the further away we are from this ith basis function that is centered at x of I, the less influential this basis function becomes for the total sum of things. And these weights then represent, in this particular, well, represents a value for MOHO depth that is close to what the actual value of the MOHO depth is at that point. So, and we will get into a little bit more detail about that in a second, right? So let's first look at polynomials, right? So this is in 1 dimension, right? So this would be, let's say, the longitude or the latitude. This is the x-axis right here. Here's our point of interest, xk. This is our point x of I, which happens to be the origin or the center of this grid. It doesn't really matter where you choose it, but you have to choose one. And I've drawn a 0th order polynomial, a 1st order polynomial, which is a line, a 2nd order polynomial, a 3rd order one, a 4th order one, etc. Right? And you can keep going with as many polynomials as you want, and you can expand them in 2 dimensions, for example. And then you keep adding higher order polynomials to this sum of functions that you use to express the continuous functions that would represent your MOHO. Right? So each of these basis functions, each of these polynomials basically covers the entire region that you're trying to model. You can do the same with harmonic functions, right? Except these polynomial functions will change into sines and cosines that each have different frequencies. But we are going to look at local basis functions that are only defined in the vicinity of a grid point, right? So let's say this is x of k. This is the point that we're interested in knowing the MOHO depth for. Then we have only 2 of these local basis functions, namely the one centered at x6 and the one centered at x7 have non-zero values at this point x of k. So the total contribution of all of these basis functions that all have height 1, by the way, to the value at this point x of k, right? It's only these 2 values from the basis function x6 and the basis function at x7 that contribute to whatever the value of the MOHO depth is at x of k, right? So we take each of these 2 basis functions, multiply them with what the MOHO depth is at each of these points, or with the weight for each of these points. It turns out that that happens to be the MOHO depth. And so let's say we have a MOHO depth at x6 that is 6 kilometers different from 40 kilometers, and x7, the MOHO depth is 7 kilometers different, right? So then the total contribution to the MOHO at x of k would be this weight times 7, which could be 1/3, because we're maybe about 1/3 away from x6 and 2/3 away from x7, and then plus 2/3 the value of x of 6, right? So that means that we have a weight that is twice as high for x of 6 than the weight that we have for x of 7, and all the other weights for all the other local basis functions are 0. So our MOHO depth here, right, will become 2 plus, 4, 2 times 2 over here, plus 2 point something, 2.3. And so maybe our total MOHO depth becomes 6.3 at this point, right? So it's 6 over here, 7 over here, and then 6.3 when we are 1/3 away from x of 6, right? So it's basically these basis functions, these triangular basis functions, represent a linear interpolation scheme. So that is one set of local basis functions. Last week, you discussed in the lecture on Kriging how these basis functions were essentially Gaussian functions or squared exponential functions. So they were a lot smoother than these, triangles that will give you a piecewise linear function, right? Between grid points, will have linear changes in whatever the total value is of the MOHO. Oopsie. But they have sharp corners, right, at each of the grid points. They can change slope. So the slope is not continuous, even though the value for the MOHO depth will be continuous. So sometimes when you need to do computations with your continuous function that represents your quantity of interest, like the MOHO depth, you actually might want to prefer smoother functions like Gaussians or squared exponentials. Those are the same thing, just different names for the same type of function. And that could be beneficial because they don't just give you a continuous function, but they will also give you continuous derivatives and continuous curvatures, etc. So they're infinitely differentiable. And that is actually a good property for some situations where you need that, right? For example, if you want to do ray tracing or something like that through a velocity model. Anyway, I like these linearly interpolated functions, and I'm going to tell you why in a second. So since we were working in 2 dimensions, right, we need to go away from the 1 dimension and look at 2 dimensions. So where our x-axis is over here on the right for both of these plots, and the y-axis or latitude axis is over here. And so these are these colors represent the height, right, of these basis functions. So this figure here gives us the height in colors, with yellow being high, right, and purple being low, of the bilinear interpolation function. And these are the colors of the squared exponential function, right? So this one has a much smoother decay towards 0. And it is basically a spherical or radially symmetric function. And so the contours of it are circles. And this one is not exactly spherically symmetric. It is also not exactly a pyramid. If you look at this carefully, so this squared exponential, by the way, it can extend beyond the grid points, right? So it can extend beyond the grid points, or it can actually be 0 before you get from the center grid point to the next grid point. So, and that basically, causes the weights that you use for these functions to not be exactly representative of the quantity you're trying to model, right? Because at any point in between here, right, you're summing the effect from this grid point that is centered here, but you're also summing an effect from other grid points that are centered here or here or here or there. And the sum of the values of these squared exponential functions from these different grid points is not going to add up to 1. So that basically is one, in my view, a slight disadvantage of these functions. The bilinear functions, you don't have that because you could see here it has a sharp edge where it actually reaches the 0 value in a square. So if you have other grid points, like here, here, and here at the edge of the square, right, and this bilinear function is defined to extend exactly to the edge, right, exactly by one grid spacing in one direction and another grid spacing in another direction. So if you have surrounding grid points and you center one of these bilinear functions on on this one, on that one, and on that one, and then you add up the values at any point, you know, in this square, the values are always going to sum up to 1. So that means that the values at these grid points represent the actual function that you're trying to model. And so, yeah, and you only need these 4 functions if you are within this grid. You don't need to worry about the other ones. So this is what the...
Before you move on, we have a question.
Yes.
So the question is that because the Gaussian is defined for all real numbers?
Because the Gaussian is defined for real numbers?
The question, so do you need to truncate because the Gaussian is defined for all real numbers?
No, you would want to truncate if you were using harmonics or polynomials, right? Because you don't want to go to infinitely high frequencies or high spatial variations. So, but these Gaussian functions or these squared exponential functions are as local as these bilinear functions, right? And in these 2 pictures, we're just looking at one singular basis function, but you have to imagine that there is a function like this on each of these grid points, right? On a whole regular grid. And my point is essentially that for these bilinear functions, anywhere you are, right? All of the functions from all of the grid points that combine together with a weight of 1 will add up to 1. Whereas for these squared exponential functions, that is not the case. Depending on where you are on your grid, you don't always get the same value. Even if you give all of the squared exponential basis functions a weight of 1, you don't end up with a continuous constant surface that has a value of 1. Did that answer the question? You can always ask more. Sorry?
Yes, it did.
Thank you. So what is this? So this kind of looks like, you know, a Gaussian function, but, you know, in 2 dimensions. And what does this function look like, this bilinear function, right? You could think it's a pyramid, but it's not exactly a pyramid. This is that function, but looked at, you know, from a perspective in 3 dimensions. So these are the latitude and longitude axes, and then in the vertical direction is the value of the basis function, right? And the tip of it is basically defined to be 1 because we're multiplying it with the weights that we need. So if you look at it from this perspective, right, it looks like a pyramid with very nice straight edges right along the grid lines and also here in front. But you could see it's a little bit more complicated than that. And if you look at it from this perspective, right, where this is a grid line and this is a grid line, you could see that it's a little bit curved over here when you go along diagonal grid lines. And so, and that is necessary in order to make sure that all of these basis functions add up to the same value of 1 wherever you are on the grid. And that is essentially why I like them. So, the math of going about this. And if there are more questions, right, about the previous, just put it in the chat, right? So these are pictures taken of that whiteboard behind me, so hopefully this is more legible. So as I said, the convenient property of these bilinear basis functions is that, you know, these basis functions are 0 for all basis functions, right, that are not, so if you are on a grid point, right, so if you want to know what the value is of a particular basis function, or of all the basis functions at x of j, which is a grid point, then basically it is 0 for all I that are not equal j. So for all other grid points, the basis functions are 0 at x of j. Except at x of j, h of j has the value of 1. So that essentially also means that, so the weight at this grid point j, right, is exactly the value of the function, in this case, the Moho depth. And I've already said this a few times because I'm so excited about it. Okay, so essentially, so the Moho depth at x of j is whatever the weights represent. So you can essentially just plot the weights, or so you don't actually even have to use them to forward compute the Moho depth. But that is what you would have to do if you were to use sort of Gaussian basis functions. And that's easy to do. It's not a big deal. But I just like this because it's convenient, right? And that also means that, like I said before, the sum of all basis functions at any point x of k is always 1. So if you were not to use these bilinear basis functions, you could use the squared exponential function or a spline function. And so then this would not be the case. And you just essentially replace this whole business of writing your continuous function as a sum of weights times basis functions. Replace it by a sum of weights times basis functions that are weighted by the sum of all the values of the basis functions at a particular point x of k, right? And this sum depends on x of k. It is different at every point. So it is slightly more computationally involved, but it's totally fine to do, of course. Okay, so we're writing this particular function here, right? And these basis functions, if we use the bilinear interpolation basis functions, these are basically these triangles or these like functions that I showed you. And so, and that basically ensures that between two grid points, there's just a linear change from the value at the one grid point to the value at the next grid point. Right, so f of x is a piecewise linear function. You also know that f of x is linear in the weights, w of I. So we can write this whole entire equation, right, as a matrix equation, because we don't just have the value f at a particular point x of k, right, but we have measurements, right, at perhaps a lot of x of k's, right, which we can group into this vector y over here, or this vector f. Represents, you know, the value of the continuous function that feeds, you know, our estimates of Moho depth y. And also, and so, yeah, this is essentially a matrix equation, right, where we have this basis function that depends on both on the point where we have the measurement, k, and the point I, which is the grid support point that we're considering for this particular basis function. Right, so we have two integers for this, which ends up in this matrix G, and then we have a vector of weights, right? So we have one weight for each grid point, and we group them all in a one-dimensional vector W right here. So this definition, right, of the function that represents our Moho depths can be written as a matrix equation right here, right? Because now we have a linear relationship between the Moho depth and the weights that we assign to each of the grid points on this regular grid. Now, this we have these measurements y, which were representative of what we think this function is of Moho depth, plus this epsilon right here, right? So if we subtract these predictions of Moho depth based on the weights that we assign w, right, and the basis functions we defined, and then the weights that we find or assign or assume or infer, you can use this to predict the values of y, to predict the Moho depths, and then we have these measurements, and the difference between them is essentially an error, and that error is what we want to minimize. So, right, so the only values of the continuous functions are at the points where we have measurements, and those measurements are grouped in this vector y. So f is a linear function of w, and that's great. And now we want to minimize each and every one of these epsilons for each and every point where we have a measurement of the Moho, right? So we want to minimize these errors. And so we need to find a w for which y is as close to these predictions as possible, or in other words, the predicted MOHO depths need to be as close as possible to the actually observed MOHO depths. And so that looks kind of fine, right? We can just say W equals the inverse of G times Y. And remember that the rows of G are filled up by the values of our basis functions, right? And the values of the basis functions in a particular row of G depend on the distance between the grid point represented by the column of G and the point where where the measurement was taken. So this is not possible, right? Because, for example, we might have a lot more grid points than we have measurements, or we might have fewer grid points than we have measurements, right? Remember those two scenarios where we had a gap in coverage and where we had a lot of measurements, clustered near a particular singular grid point. So we can have both situations. And so this matrix G is not square, and it's probably singular, just like we discussed last week during Dr. Lowry's lecture. So we can't simply take its inverse. So instead, what do? Let's minimize the length of this vector epsilon, which is the difference between the data and the observations. So that would be this vector right here, and we take the square of it. So that we are not bothered by whether the difference is positive or negative. And so we call that quantity uppercase E of W, and we want to minimize this. But now remember that Y was a linear function of W, therefore E, which is a function of the square of the length of that difference vector, E is now a quadratic function of W. Right, and this is what that looks like. So there's a lot of terms in this function. And so as you have done many times for parabolas, you can find the minimum of a quadratic function by taking the derivative and figuring out for which W that derivative is equal to 0. So that's what we're going to do here. Well, we're not actually going to do it, but that is how you would do it, right? So you take the derivative of E to a particular weight at grid point K, and you evaluate what that is, right, using this equation right here, and you set that to 0. Then you do it for the next value of K, right, for the next grid point, and then the next, and the next, and then you do this for all grid points, all values of K. And the answer is this, right? Essentially, your weight vector W becomes you take your observations Y and you sort of project them to the weight space from the data space in which vector Y lives. You project them to the weight space, and then you multiply with the inverse of G transpose times G, and that gives you the best solution for W. This is the least square solution for W. And you can do that derivation and arrive at this answer. And but if you want a shortcut, then look at this green font right here. The trick is to remember that we have the data that we want to equal to the predictions, right? Or vice versa. We want these predictions over here, G of W. We want those to be as close to the data Y as possible. So we know we can't invert G, so we just simply multiply the left and the right hand side of this equation with G transpose. And then we simply take this G transpose G, which is now a square matrix. We multiply it with its own inverse. So on the right hand side, we're left with W, and on the left hand side, we have this, right? So if you can remember this trick, you will always know what the least square solution is of a linear equation. But what now if we have errors in Y, right? What if these errors in Y are not the same, right? The MOHO depth estimate in one point where, a station might have been only operating for like 2 months will be a lot more uncertain than the MOHO depth under a permanent station that has been operating for decades. So these standard deviations, these error estimates for data Y, are going to differ, right, as a function of measurement. So sigma 1 squared might be different from sigma 10 squared, for example. So we group all these in a sort of diagonal matrix, and that we call the data covariance matrix. We can then weight the left and right-hand side of our equation with the inverse of the square root of these measurements, right? So basically, essentially, we take measurement y of k and divide it by the standard deviation or the for y of k, right? Or the standard deviation is the error estimate for y of k. So every single measurement is down weighted by its uncertainty. So if one measurement is very uncertain, then the effective number here becomes smaller, right? So we're changing the units of y from kilometers to standard deviations. And then when we are minimizing the sum of the squares of the differences between the predictions and the data, we're essentially minimizing the quantities in units of standard deviations. So that helps give the data that have smaller uncertainties, it helps to give them more weight in the inversion, right? So, you know, that least square solution is basically the solution of an inverse problem. So that's the result of the inversion. So we multiply the left-hand side by the inverse errors, and we have to do the same on the right-hand side. So this matrix combination we can call G prime, and this new data vector we can call Y prime. And then we have a familiar equation with a familiar solution. Now, if you take these definitions for G prime and Y prime and you fill them in here, right, you'll see what this amounts to in terms of the actual matrix G and the actual data vector Y. Also, we can have prior expectations for the weights, essentially for the MOHO depth, right? And in this particular case, right, we expect the MOHO to vary by a certain amount, right? Especially in places where we don't have measurements, we still have a certain expectation that either the MOHO is similar to the MOHO farther away from it, or we know it's got to be 40 kilometers on average for continents, for example. So we want the MOHO depth to be as close to 40 kilometers as possible. And so we can basically decide how much we want the MOHO to deviate, right? And these could all be different actually from, you know, from the average, right? So maybe we could say beneath mountain ranges, we expect larger deviations than between plains that have no topography, for example. Or we can base our prior expectations of MOHO, for, you know, deviation from the average MOHO. We can base it on gravity measurements, right, as we looked at last week. So what is reasonable? What is a reasonable expectation? A few kilometers? Sure. 10 kilometers? Maybe. 40 kilometers? That would put the MOHO at 80 kilometers or at 0 at sea level. And that is very, very unlikely. And so that becomes less likely, right? So there's definitely a reasonable choice you can make for this value of a squared. And in the lab notebook, we're using a squared equals 9, right? So it's pretty conservative. That means, you know, we expect the MOHO to deviate, you know, 67% of the time by 3 kilometers. So if you do that, you don't just have your data needing to equal G times W, but you also want W times this model covariance matrix, the inverse of it, and then the square root of the diagonal elements. You want that to be as close to 0 as possible, where W here is not the MOHO depth itself, but the deviations from the average of 40 kilometers. And then again, we can call this, right? And some of you might recognize this as damping, for example. This Cm minus 1/2, right, this inverse square root of the model covariances does not have to be a diagonal matrix. It could contain constraints on the first derivative, for example, the differences between the weights for neighboring grid points, for example. So we can call this combined matrix G prime again, and this combined data vector Y prime. And again, we have this solution that we're now familiar with. And when you combine the two, this is what it amounts to eventually, right? And so here we have the data covariance matrix wedged between the GT and the G. the model covariance matrix or the inverse of it is added before we take the inverse. And again, the data are also weighted by the inverse variance of the data itself. So this is our most formal estimate of the deviations of MOHO depth by using this inverse method. So this will at the same time deal with data errors that are not drawn from the same distribution, right? Giving you data that are more uncertain, data that are less uncertain. And so, and indeed, we do have more precise or accurate knowledge of some MOHO depths than we have of others. But it also helps to deal with spatial gaps in the data, right? Where we have blank regions and no measurements. In that case, right, and in the way we're implementing it using a diagonal covariance matrix for the model, for the model covariance matrix, basically we are assuming the simplest MOHO that is consistent with prior knowledge. And for the purposes of this exercise, our prior knowledge says the MOHO under a continent should be 40 kilometers. Obviously, we might know more about the MOHO than that, but for in this exercise, we pretend we don't. Right? So essentially, we're damping the MOHO to 40 kilometers in the absence of other knowledge given by this data vector y. But as I said before, we can do first derivative damping or first derivative, first derivative regularization, or we can do smoothing, which adds components of the curvature of the continuous function in this model covariance matrix. So there's a lot of freedom that you have with that. All right, any questions about this part before we go on to the data?
No, you don't have any questions.
All right, so I'm sorry I either talked over your heads or you knew all this already. The data. Remember, you can also ask questions during the lab. Anyway, so this was the map. I already explained what the colors are, right? They represent MOHO depth according to this scale that is estimated from lots and lots of seismograms by this project EARS. And so this data are basically downloaded from the EARS data service that is hosted by IRIS. This is the map I made of them. I know that some of you have made other maps using different color bars, for example. And they all looked fabulous to me, the ones I've seen. So here's where I've used, pi GMT, not pGMT. And, but these data were downloaded at a slightly earlier date, I think last year, right? Compared to this map on the left that I downloaded yesterday. And this is the one I downloaded last year. And you see that they're not all that different, right? You can clearly see this red dot here in Nevada, right? This map has state boundaries. This is the one that Dr. Lowry focused on in his lecture last week, for example. And there's other very interesting things. If you know anything about the geology of the United States, right, you can clearly see the Basin and Range province in here, which is kind of really interesting. You can see mountain ranges with deeper MOHOs, right? The Rocky Mountains, the Cascades, and the Sierra Nevada, even the Appalachians, and and then the Grenville to some extent. They have interesting MOHO depths right here. And then here, right, this is a very significant chunk that was taken out of the Laurentian Craton that that forms the core of the North American Craton right now. This piece that was taken out is actually now in Argentina, which is amazing, right, when you think about it. Anyway, so there's lots of things here that we can see, but at the same time, you could see a lot of variation here, right? This is not a very smooth continuous functions. There's also a cluster here of very dense points of MOHO depths. And then there's clashes in color as well, right? So when we start gridding this, we can deal with all of these sort of incompatibilities, right? Let's say that the MOHO in nearly one and the same place needs to be both deeper and shallower than average, which is of course challenging to do. And so, and not realistic if you think about how these estimates were made, right? From ray paths that come from multiple directions and essentially sample sort of the same MOHO. Anyway, so the gridding will deal with all these incompatibilities. And it will also fill in gaps. For example, it will tell us some information about Canada that may or may not be correct, or about Mexico that may or may not be correct. However, we are going to split this whole data set actually in two different data sets. One data set that has non-US array, non-transportable array stations, MOHO depth estimates for these stations, and another set that has MOHO depth estimates for pure US array transportable array stations. And we're going to use one of the sets, this one, to predict the MOHO depth for the other set via gridding specifically. So this is the split. On the left, right, we have all of the estimates of MOHO depth for all stations that are not labeled as transportable array stations. This, of course, includes flexible array stations to some extent. And then on the right, we have all the MOHO depth estimates for transportable array stations. And we're just going to do, for fun, you're going to use all of these measurements and use them to predict what the MOHO depth should be at this sort of semi-evenly spaced grid, right, of TA station locations, and then compare it with the actual estimates at these station locations. So first, I applied the technique we learned last week. I used these points on the left here, right, that I call the training data. And I basically applied kriging to get this data set or not data set, but these values of MOHO depth predictions at the locations of the transportable array stations of US array. And these were the actual measurements. So interestingly, right, you can see that there is some agreement, right, quite a bit of agreement here, for example, for the Basin and Range province here. And that is understandable because we actually have some measurements for that province as well. And it is, this whole chunk here is coming out from these because we have measurements right here, right? And then we have that chunk indeed in the data as well. But then if you look at this part, right, of the United States, where there's very few MOHO depth estimates from very few stations, right, we see that mostly it's all green, right, except where we have a few blue dots, we have a little blue blob here, but there's a lot of green right here, which is 40 kilometers, right, which was our sort of prior knowledge of where the MOHO should be in the absence of better information. Like we don't have information here. So essentially we end up with a green 40 kilometer deep MOHO, which is completely not consistent with what the transportable array data are telling us, right? So predictions are good where we actually have constraints from data, and predictions are not so good where we didn't have enough data. Very understandable. So we can also simply say, well, for every point here, why don't I just weight the influence from neighboring stations, right? So I go like, I don't know, to a point right here, and I see I'm nearby this blue dot and that blue dot and that turquoise dot and these other blue dots. And I'm going to maybe assume the squared exponential functions, Gaussian functions, and depending on how far away these dots are, I'm going to take these MOHO depth value weighted by whatever the function value is at my point of interest, right, of this squared exponential function, and then add to that the influences from all these other points, again weighted by the value of the squared exponential function that depends on the distance. And then I'm going to divide by the sum of all these function values so that they add up to 1. And then I'm going to estimate my point right here. And I can change the radius of these functions, right, to include more points or fewer points, for example. And I can do that at every point right here. So if I do it here, I end up averaging all of these points. And if I do it here, right, I end up maybe only using this green point right here. So that is something we're also going to do in the lab notebook, and you will end up with a map more or less like this, right? And it shows similar features. It's actually not bad. It's actually pretty good. It does similarly to what the kriging did for us, and in terms of comparing to the actual observations. So, and then we move on to gridding, which is based on the inversion that I covered the maths of. And so this is a grid, right, of all of the regularly spaced MOHO depth values at regularly spaced points. And this grid is plotted at the native resolution of 1 by 1 degree. And so this map is now the predictive map, you know, for that we can use to compare to these points of the TA stations, right? And again, we see the same features we saw before, by the way, on the native resolution. However, remember that every grid point doesn't necessarily represent some sort of step staircase of a constant value. It is actually defined as piecewise linear. So in order to sample this continuous function, I actually need to sample it on a finer grid than the resolution of the support points of the grid. So when I do that, I get this map right here, right? This is just the same function, but more finely sampled, right? So I'm not, so I'm basically properly sampling this function rather than coarsely sampling it. And this is what that map looks like. So again, right, we find green areas here where we didn't have a lot of data that don't necessarily agree with the independent sort of testing data, but where we do have data on the East Coast, in the Western United States, we have, you know, reasonable predictions here from this gridding, just like we saw with the other two methods. So I think it's time.
Suzan, we
Yeah.
have a question on the previous slide. So the question is, it looks like there's an orange dot in Wyoming-ish in the training data, but it is no longer in the predicted. Can the prediction change the training data?
Okay, an orange dot in Wyoming.
I think maybe up, it's kind of isolated. There's an orange and a blue in the, almost where your mouse is. Go down a little bit further. Yeah, I think that's what I would guess. Yes, that one. And so that is no longer in the prediction.
Well, it's not in the grid because the grid essentially averaged those two out. So the grid is saying, let me see, that will be here-ish, right? And the grid is saying, well, that's pretty much green, you know? And so it's weighing sort of the average of these 2 points. If these 2 points have high uncertainties, right, they are going to weigh less than our prior knowledge that says that the MOHO needs to be 40 kilometers right here. So it could be a combination of factors that makes this area green, right? It could be that it's dominated by prior knowledge, or that the average of these 2 points is simply green, or both. But my guess is that these have higher uncertainties. And one part in the lab is that you're going to plot the uncertainties on a map as well. And you're going to make this thing in the lab as well, right? So you can actually do your own research into these 2 points to figure out why they, lead to a green grid point, essentially. So in the lab, what are you exactly going to do? First, you're downloading the EARS data, and you can actually download your own data set. You don't have to use the one that I posted on Slack. If you use the one that is posted on Slack, you have the exact same file that I used. So that may or may not be an advantage. Then we're going to split the EARS data set into an estimates for use array stations, or more specifically, transportable array stations and other stations. Then we're going to explore different ways, right, of using these data to predict the MOHO depths. First, without gridding, and you're not going to do kriging because you did that last week, but we're going to do the weighted nearest neighbor sort of averaging on a regular grid. And then we're actually going to use gridding using an inversion, right, using bilinear basis functions and a 1 by 1 degree grid. So the detail on point B, which is kind of sort of the focus of this lecture, is we're going to define these basis functions. We're going to use the non-transportable array data and their error estimates, right, to weight them properly, as well as prior expectations for the MOHO, which we simplify to saying, well, the MOHO should be 40 kilometers unless we have an estimate that says otherwise. And then we're going to infer optimal weights. And that is the inversion that we're going to do. And then we're going to use these weights to predict the MAHO for the TA stations, or you are going to do that. You're going to calculate the fit, right? How good are these predictions, right? How much did you even need the transportable array? Could we have just mapped the MAHO with all the other stations? Of course, it's a slightly false sort of comparison because all the other stations are part of, a lot of these other stations are actually part of US array as well, except they're not called transportable array stations. But in some of them were even installed sort of afterwards, right? So anyway, but it's a fun exercise to do. And then there's more details, obviously, in the lab notebook that we're going to get to. So before we start that, after probably a small break, during which I can upload all this to Slack, are there any questions?
I don't think we have any questions.
Well, in that case, I apologize.